At the edge of everything we can see, there is an invisible frontier that feels like the universe's final secret. Imagine looking out across the vastness of space and finding not an edge of stone or steel, but a horizon made of pure mystery, a boundary beyond which no telescope, no signal, and no human eye can ever reach. Scientists call it the cosmic horizon, the farthest limit of the observable universe. From Earth, it looks like the universe is 93 billion light-years wide, with us sitting in the center, but this wall we see is not really the end. It's not that space stops there, it's that light itself cannot travel any farther to reach us. Beyond this veil, galaxies, stars, and unimaginable worlds continue on, hidden forever from our view. And yet, even though we will never directly see them, the question lingers: what lies beyond this horizon? The answer could change everything we think we know about reality. To understand this mystery, picture standing at the edge of a cliff in thick fog. You can only see a certain distance, and the rest disappears into blankness. Move to a new spot, and the fog shifts, revealing different parts of the landscape. That's how the universe works. Every observer has their own horizon, their own visible slice of the cosmos. Our horizon isn't unique. An alien scientist in a faraway galaxy would see an entirely different map of stars. This means that what we call the edge is not really an edge at all. It's just a personal boundary, a limit imposed by the speed of light and the age of the universe. And if space continues far beyond what we can see, then our observable universe is nothing more than a raindrop in an ocean too vast to measure. Already, astronomers suspect that for every galaxy within our horizon, there may be at least 23 more beyond it. That means hundreds of billions of galaxies, each with trillions of stars, are forever invisible to us. Among those hidden worlds could be alien civilizations that have risen and fallen long before we existed, suns so enormous they would dwarf ours into insignificance, and planets with skies painted in colors that human eyes have never seen. Beyond our horizon lies a cosmic wilderness, untamed and unknowable, but the greatest twist of all is that this horizon is not fixed. It grows. Every moment, light from slightly farther away finally reaches us, stretching our boundary outward by 6 trillion miles per year. To us, that sounds vast, but in cosmic terms, it is barely a step. Our map of the universe expands constantly, yet we will always be limited, chasing a horizon we can never catch. But the horizon itself whispers secrets. The faint glow of ancient light, the afterglow of the Big Bang, bathes the entire sky, a fossil from when the universe was only 380,000 years old. This cosmic microwave background acts like a photograph of the infant universe, showing us patterns and structures that reach far beyond what we can see. These patterns hint at a hidden architecture, a universe larger than we imagined, maybe even infinite. They whisper about colossal structures bigger than any galaxy, about dark matter scaffolding that holds the cosmos together, about invisible forces like dark energy that are stretching space itself apart. Some anomalies in this ancient light even hint at collisions with other universes, scars left by realities beyond our own. And suddenly the question grows even deeper, not just what lies beyond our horizon, but whether our universe is only one of countless others. This is where the mystery becomes overwhelming. What lies past the edge may not just be more stars and galaxies. It could be entire parallel universes born in an endless inflation of space. Realms where the laws of physics are different, where time itself flows differently, where the impossible becomes routine. Or perhaps the horizon marks something even stranger, a holographic surface where all the three-dimensional depth we experience is just a projection of data encoded on a distant boundary. Or maybe, in the most unsettling possibility of all, Everything we see is not physical at all, but part of an advanced simulation. Reality is information running on a machine beyond comprehension. Standing at the edge of what we can see, the cosmos confronts us with a paradox. We are small, fragile, temporary beings, and yet we have discovered that the universe is so vast, it might contain infinities, stacked upon infinities. But the fact that we can even ask these questions gives us significance. We are not just lost in the void. We are the part of the universe that looks back at itself and wonders, and as we gaze across this horizon of light, one truth becomes clear. The edge of the universe is not an end at all. It is an invitation, a challenge to curiosity, and the beginning of a journey into mysteries deeper than imagination itself. When we talk about the edge of the universe, most people imagine some kind of wall, a barrier beyond which space itself simply ends. But the truth is far stranger and far more fascinating. The edge we speak of is not the end of space at all. It is the edge of visibility, a boundary set by the limits of light and time. This invisible frontier is called the cosmic horizon, and it stretches around us in every direction like the surface of an enormous sphere. At its current size, that sphere is about 46 billion light-years in radius, meaning the observable universe spans roughly 93 billion light-years across. It might sound odd that the observable universe is so much larger than the universe's actual age would suggest. After all, the universe is about 13.8 billion years old, so how can we see 46 billion light-years away? The answer lies in the expansion of space itself. While light has been traveling toward us for nearly 14 billion years, the space it traveled through has been stretching the whole time, pulling those distant galaxies even farther away. What we see is not where they are today, but where they were when their light first began its journey toward us. To understand this, imagine light as a messenger traveling across a rubber band while the band is being stretched. The messenger keeps moving forward, but the band itself expands beneath them. By the time the messenger reaches you, the starting point is much farther away than the distance they originally traveled. That's what's happening on a cosmic scale. Every distant star, every galaxy we see, is a glimpse into the past, and the farther away we look, the further back in time we peer. A galaxy a billion light-years away is seen as it was a billion years ago. Look farther still, and you see galaxies as they were billions of years earlier, their light having raced through the cosmic dark for almost the entire age of the universe. Eventually, if you look far enough, you reach a point where the light has been traveling since the universe was only a few 100,000 years old. That point is the cosmic horizon, the farthest back in time we can ever see, because before that, the universe was too dense, too hot, and too chaotic for light to travel freely. It's a sobering thought. The cosmic horizon is not a physical wall, not a place where the universe ends. Instead, it is the limit of our vision, a reminder that we are always peering into the past. Every photon captured by a telescope is a message from long ago, and the universe we observe is really just a cosmic memory. The stars we see are often long dead, the galaxies reshaped or gone. Even the horizon itself is not fixed. It expands outward as new light finally reaches us from slightly more distant regions. Every second, our observable sphere grows by about 300,000 kilometers in radius, the distance light travels in that time. Over the course of a human lifetime, the horizon expands by about 6 trillion miles. That sounds impossibly large, but in cosmic terms, it is barely a blink. For all our progress, the universe will always keep most of itself hidden beyond that unreachable frontier. The strangest part is that the cosmic horizon is unique to every observer. Just as someone standing in a foggy field has their own circle of vision, every point in the universe sits at the center of its own observable sphere. An alien scientist in a galaxy near our horizon would see a completely different map of stars and galaxies than we do. Their horizon would overlap with ours in some regions, but also include cosmic territories we will never observe. This means that no single observer ever sees the full universe, only their personal slice, limited by time, distance, and the speed of light. And if you put all those perspectives together, the true universe may be staggeringly larger than anything we can imagine, perhaps even infinite. But perhaps the most humbling realization is that the horizon is not just a barrier to our sight, it is also a barrier to our knowledge. Beyond it, galaxies continue to exist, stars continue to burn, and planets may orbit suns under alien skies. But no matter how powerful our telescopes become, we will never see them. They are forever cut off by the laws of physics themselves. We live in a universe where much of reality is hidden, and yet even within that narrow band of visibility, we have uncovered extraordinary truths. The cosmic horizon is both a limitation and a gift. It tells us where our vision ends, but it also provides the map of everything we can possibly know. And as we press against this boundary with science, with imagination, and with questions that stretch beyond the limits of light, we are reminded that this edge is not the end of the story. It is the beginning of an even deeper mystery. If the cosmic horizon is the edge of what we can see, then what lies beyond it must be one of the most tantalizing mysteries in science. Imagine staring into the night sky and knowing that for every galaxy twinkling faintly in the darkness, there are perhaps 24 more that remain forever invisible, hidden behind the curtain of distance and time. This is not speculation pulled from imagination. It's a conclusion drawn from the very laws of physics and the growth of the universe itself. Scientists estimate that for every galaxy within our observable reach, there may be at least 23 more beyond it, unseen and unreachable, existing in a realm of the universe that light has not had enough time to deliver to us. This means that what we perceive as the universe is really just a sliver, a thin slice of an unimaginably larger whole. The stars and galaxies we see are like islands at the edge of a vast archipelago, while the rest stretches endlessly into the fog of eternity. But hidden doesn't mean empty. Beyond our horizon, space continues to teem with galaxies, stars, planets, and perhaps civilizations. These galaxies follow the same physical laws as ours, spinning in elegant spirals or colliding in violent cosmic mergers. They cluster into webs of structure, vast filaments of matter stretching across billions of light years, shaping the hidden universe just as they shape the part we can observe. Some of these galaxies host stars far more massive than any we know, burning brighter and dying younger, leaving behind black holes that may grow into monsters larger than entire solar systems. On planets in those galaxies, alien skies could blaze with colors our eyes cannot even detect, painted by suns with different chemical compositions and atmospheres filled with gases unknown to us. Life, if it arose there, would have evolved under rules that would appear foreign, perhaps even unrecognizable. The strangest part about this hidden universe is that it isn't static, it is alive with expansion. As time passes, light from more distant regions slowly arrives, pushing the horizon outward. Every second, photons that began their journey billions of years ago finally reach Earth, adding a tiny fraction to the cosmic map. But the universe is also expanding faster than light can travel, which means that beyond a certain point, galaxies are racing away from us, so quickly that their light will never catch up. Those galaxies are not just hidden, they are gone from our universe forever, carried beyond reach by the relentless acceleration of cosmic expansion. In this sense, our observable universe is like a bubble floating in an infinite ocean, and every moment, new cosmic territory enters our bubble, even as other galaxies slip away beyond its edge, never to return. Another strange truth is that every observer in the universe has their own hidden cosmos. An astronomer living in a galaxy near our horizon would see regions of space invisible to us, just as we see regions invisible to them. Each perspective reveals a different version of the universe, like countless overlapping maps of an endless territory. If you could somehow gather the horizons of every observer, stitched together like a cosmic quilt, you might begin to see the true scale of the universe, a structure so vast that it makes even our 93 billion light-year bubble seem like a grain of sand on an infinite beach. The hidden universe also plays tricks on our intuition. Many people imagine the edge of the universe as a sharp boundary, like the edge of a map. But beyond our horizon lies no end, just more of the same, stretching outward in every direction. It is as if we live inside a fog where the fog itself is expanding, and though we can never see beyond its limits, we know the landscape continues. The galaxies beyond may be nearly identical to ours, or they may have taken different paths of evolution, shaped by subtle variations in the distribution of matter and dark energy. Either way, they exist, forming part of a cosmic whole that dwarfs our imagination. This idea that most of the universe is invisible to us forces us to rethink our place in it. Our visible cosmos feels vast, with trillions of stars and galaxies, but it may be only the tiniest fragment of what actually exists. The hidden universe is not an empty void, but a realm filled with wonders we will never touch, a reminder that reality is far larger than the part revealed to human eyes. And it is this unseen expanse that raises the biggest question of all. If so much of the universe lies beyond our view, what hidden structures, forces, and mysteries might it contain? If the hidden universe beyond our sight is the great unknown, then the cosmic microwave background is the faint but powerful whisper that offers us a clue. Imagine turning on an old television, the kind with static snow filling the screen when no signal comes in. About 1% of that static is not electronic noise. It is ancient light radiation that has been traveling across space for almost 14 billion years. This faint glow, stretched into microwaves by the expansion of the universe, is the afterglow of the Big Bang itself, the fossil light of creation. It fills the entire sky in every direction, wrapping us in a cosmic memory so vast and so old that it predates the first stars, the first galaxies, even the first atoms as we know them. It is called the cosmic microwave background, or CMB, and it is one of the most important discoveries in the history of science. To understand why, we need to journey back to the earliest era of the universe. In its first few 100,000 years, the cosmos was not the clear and starry place we know today. It was hot, dense, and opaque, a seething plasma where particles of light could not travel more than a few centimeters without being absorbed or scattered. The entire universe glowed like the surface of the sun, but that light was trapped, bouncing endlessly inside a fog of particles. Then, about 380,000 years after the Big Bang, the universe cooled just enough for protons and electrons to combine into hydrogen atoms. This event, known as recombination, suddenly made the universe transparent. For the first time, light could travel freely across space, no longer imprisoned by constant collisions. Those photons have been racing outward ever since, stretching into microwave wavelengths as space expanded, and today we see them as the CMB, the first visible snapshot of the universe's infancy. What makes the cosmic microwave background so extraordinary is the information it carries. To the naked eye, it might appear uniform, a smooth glow across the sky, but when scientists mapped it with precision instruments like the COBE, WMAP, and Planck satellites, they discovered it was not perfectly smooth at all. It was filled with tiny temperature variations, differences of just a few millionths of a degree. These small fluctuations were not random noise, they were the seeds of everything. They revealed where matter in the early universe was slightly denser or slightly thinner, tiny differences that gravity would later amplify into galaxies, clusters, and a cosmic web of structure that fills space today. In those patterns, we can read the blueprint of the universe. Even more astonishing, the CMB tells us about what lies beyond our horizon. The largest features in this ancient light stretch across distances bigger than the observable universe itself, hinting that the structures of the cosmos extend far into the hidden realms we will never see. These vast patterns act like shadows cast from beyond the horizon, clues that the universe is much larger than the piece visible to us. Some anomalies in the CMB, like the so-called cold spot, a region unusually empty and cool, may even suggest that our universe brushed against others, collisions between cosmic bubbles that left faint scars in the sky. If true, then the CMB is not only a photograph of our early universe, but also evidence of the multiverse itself. The CMB also reveals something fundamental about the shape of space. By studying how its fluctuations spread across the sky, scientists can measure whether the universe is curved like a sphere, bent like a saddle, or flat like an infinite plane. The answer is striking. Within incredibly tight margins, the universe appears flat, and in cosmology, flatness implies infinity. This means the regions beyond our horizon are not just a little larger than what we can see, they may stretch forever, endless galaxies scattered across infinite space. Perhaps the most profound aspect of the cosmic microwave background is how it connects us to time itself. When we look at it, we are seeing not just light, but history. The universe as it was when it was still in its infancy. That ancient glow has crossed the whole of time and space to reach us, carrying with it a message that says, this is where everything began, and though we cannot see beyond our horizon, this light gives us a window into realms far larger than we can ever directly observe. A reminder that the cosmos is not only vast but deeply connected, its earliest moments still echoing all around us. The CMB is the oldest light in the universe, but it is also a doorway, pointing toward questions far more radical than simple beginnings. It tells us that the universe once expanded faster than light itself, that quantum ripples in the smallest fractions of a second were stretched into the largest structures in existence, and that beyond our horizon may lie infinite other worlds. The afterglow of the Big Bang is not just a relic, it is a clue, a whisper across eternity, inviting us to keep searching for what lies beyond. The idea that our universe is vast is already staggering, but the possibility that it might not be alone takes the mystery to an entirely new level. This is the concept of the multiverse, the idea that our observable cosmos, with its billions of galaxies and trillions of stars, may be just one bubble in an endless ocean of universes. It sounds like science fiction, but it emerges naturally from the physics of cosmic inflation, the brief but violent expansion that occurred in the first fraction of a second after the Big Bang. During this moment, space itself ballooned at a rate faster than the speed of light, stretching quantum fluctuations into vast structures that would become galaxies. Inflation explains why the universe looks so smooth and uniform across vast distances, but it also suggests something far more radical, that inflation may not have ended everywhere at once. Instead, it could still be happening in distant regions, creating new universes in an eternal cycle. To picture this, imagine a pot of boiling water. Tiny bubbles form, grow, and separate from one another. In this analogy, each bubble is a universe with its own laws of physics and its own cosmic history. Our universe is just one bubble among countless others, expanding in a frothing sea of creation. Some of these universes might look much like ours, with galaxies, stars, and planets. Others might be utterly alien, governed by different laws of nature, where matter clumps differently, where time flows strangely, or where the basic building blocks of reality are not atoms, but something entirely unimaginable. In some bubbles, stars might never form at all, leaving a dark cosmos filled only with diffuse gas. In others, the force of gravity might be so strong that everything collapses into black holes almost instantly. The multiverse is not just a bigger version of space, it is a realm of infinite variation. What makes this more than wild speculation is that the cosmic microwave background may carry scars of these cosmic neighbors. Some anomalies in the ancient afterglow of the Big Bang, strange cold spots, and unusual alignments could be evidence of collisions between our universe and others. If two bubble universes formed close enough during inflation, they might have smashed into each other, leaving imprints in the fabric of our cosmos. While the evidence is not conclusive, even the possibility that we are seeing the fingerprints of other universes is enough to transform how we think about reality. The multiverse also offers an explanation for one of the strangest puzzles in science: why the laws of physics in our universe seem so perfectly balanced for the existence of life. The strength of gravity, the charge of the electron, the speed of light, these values appear fine-tuned, delicately arranged, so that stars can form, planets can orbit, and chemistry can unfold in ways that allow living beings to exist. In a multiverse, this isn't surprising. If countless universes exist, each with different physical constants, then it is inevitable that some will have the right conditions for life, while most will not. We just happen to live in one of the rare universes where everything lined up correctly, because otherwise we would not be here to ask the question. This idea is unsettling because it implies that much of what we consider fundamental might not be fundamental at all. The laws of physics we see could simply be local rules, applying only to our universe. Somewhere else, other rules may dominate. Space might have more or fewer dimensions, time might behave in non-linear ways, and reality itself might be structured around principles that are completely foreign to us. The multiverse transforms our understanding of the cosmos from a single grand stage to a limitless theater where every possible play is performed. But perhaps the most dizzying thought is this: in an infinite multiverse, every possible version of events must occur somewhere. There could be universes where Earth never formed, universes where civilizations far older than ours solved the mysteries of existence billions of years ago, and even universes that are eerily similar to ours, where another version of you is reading these words under slightly different circumstances. The multiverse challenges not only our view of science, but our sense of identity and uniqueness. For now, the multiverse remains a hypothesis, an elegant idea that may never be fully proven. But whether or not it is true, the possibility itself expands our imagination beyond measure. It forces us to confront the idea that the cosmos is not only bigger than we think, but stranger, richer, and more varied than our minds can comfortably hold. And even if our universe is just one bubble among countless others, it is our bubble, our reality, and the place where we stand on the edge of mystery, looking outward into an infinity of possibilities. When we look at the night sky, we see stars, galaxies, and glowing clouds of gas. Yet all of that light, all of the matter we can observe directly, is only the tip of the iceberg. The majority of the universe is made up of something invisible, something that neither shines nor absorbs light, and yet exerts a gravitational pull strong enough to shape the cosmos itself. This hidden substance is called dark matter, and it is one of the greatest mysteries of modern science. Though we cannot see it, we know it must exist. Because without it, the universe as we know it would not hold together. Galaxies would spin apart, cosmic structures would never have formed, and the patterns we see in the distribution of galaxies would make no sense. Dark matter is the invisible scaffolding of the universe, an unseen skeleton upon which everything else is built. Evidence for dark matter first appeared in the 20th century, when astronomers noticed galaxies spinning too fast. If the only mass in those galaxies was what we could see, the stars, gas, and dust, they should have torn themselves apart long ago. Something unseen was holding them together, an invisible halo of mass providing the extra gravity needed to keep everything bound. This discovery spread across scales. Galaxy clusters, the largest structures in the universe, also showed signs of hidden mass. Then came the most striking evidence of all, gravitational lensing. Light from distant galaxies bends as it passes through regions filled with dark matter, distorting into arcs and smears. We cannot see the dark matter directly, but we can see how it bends space itself, warping the path of light like glass. What makes dark matter even more fascinating is that it appears to dominate the architecture of the cosmos. Computer simulations of the universe show that dark matter forms vast webs of filaments stretching across billions of light years, connecting galaxies like beads along invisible threads. These filaments intersect at dense nodes where galaxy clusters form, creating cosmic cities suspended in a lattice of darkness. Between the filaments lie enormous voids, regions almost completely empty of galaxies, shaped by the gravitational dance of dark matter. In this way, the universe resembles a cosmic spider web, and it is the dark strands that give it form. But what is dark matter made of? That is the mystery that has eluded us for decades. It could be composed of exotic particles, perhaps ones that barely interact with normal matter, streaming through our bodies and our planet every second by the trillions without leaving a trace. Some theories suggest it could be made of primordial black holes, tiny remnants from the early universe. Others propose particles far beyond anything we can detect with current technology. Whatever its true nature, dark matter does not behave like the ordinary matter we are familiar with. It does not clump into stars or planets. It does not emit radiation, and it interacts with the visible world only through gravity. In many ways, it is like a ghost passing through the universe unnoticed, but shaping its destiny all the same. Perhaps the most haunting thought of all is that most of the universe's matter exists in dark form. For every ounce of visible matter, every star, every planet, every human being, there are 5 times as much in dark matter. This means that everything we have ever seen, every image captured by every telescope, is only a fraction of what exists. The true universe is built from shadow. Entire structures of dark matter may exist that are invisible to us, hidden galaxies formed entirely from this unseen substance. If such ghost galaxies exist, they could be drifting right next to us, invisible but real, their presence betrayed only by the faint tug of gravity. Dark matter kingdoms are not just a curiosity, they may be the true rulers of the cosmos. While stars burn briefly and galaxies flicker in and out of existence, dark matter endures, shaping cosmic evolution across billions of years. It guided the first clumps of matter that became galaxies, and it will continue to shape the universe long after the last stars fade. Beyond our horizon, the hidden universe may be dominated by vast empires of dark matter, massive structures so immense that our entire observable cosmos could fit within a single one of their halos. In this sense, dark matter is not just a puzzle. It is a reminder that reality is far stranger than we can see, and that most of the universe lies forever in shadow. For much of the 20th century, astronomers believed that the universe's expansion, set in motion by the Big Bang, must be slowing down. Gravity, the force pulling matter together, was expected to gradually decelerate cosmic growth. Some even speculated that expansion might eventually stop and reverse, collapsing the universe back into a fiery Big Crunch. But in the late 1990s, 2 independent teams of astronomers studying distant supernovae made a discovery so shocking it overturned this assumption. Instead of slowing down, the universe was speeding up. Galaxies were not just drifting apart, they were accelerating away from each other at ever-increasing rates. The culprit was something entirely unexpected, a mysterious force now called dark energy. Dark energy is unlike anything we know. It makes up about 70% of the entire universe, yet we have no clear understanding of what it is. Unlike dark matter, which pulls things together with gravity, dark energy pushes everything apart. It acts as a kind of anti-gravity, an invisible pressure stretching the very fabric of space itself. What makes it even stranger is that its density seems to remain constant even as the universe expands. Ordinary matter and radiation become thinner as space stretches, but dark energy does not dilute. The more space there is, the more dark energy exists, and the stronger its influence becomes. This is why expansion is accelerating. The further galaxies are, the faster they are being pushed away by this repulsive force. The implications are staggering. It means that much of the universe is already lost to us. Galaxies at the farthest reaches of our view are being carried away so quickly that their light will eventually never reach us again. Over time, the observable universe will shrink in terms of what we can access, even as space itself continues to expand. Billions of years from now, distant galaxies will vanish beyond our cosmic horizon, leaving only the faint glow of our local group of galaxies. Future civilizations may look into the night sky and see only emptiness, unaware of the vast universe that once surrounded us. Dark energy is writing the future of the cosmos, and that future looks lonelier and colder with every passing moment. Scientists have proposed several possible explanations for dark energy. One idea is that it is simply the energy of empty space itself, a property predicted by quantum mechanics called the vacuum energy. Another possibility is that it arises from a new kind of field permeating the universe, one we have not yet detected. Some theorists even suggest that our understanding of gravity itself may be incomplete, and that what we call dark energy is really a sign that Einstein's theory of general relativity needs revision. Whatever the truth, the fact that dark energy is so dominant raises profound questions about the nature of reality. Why does it exist at all? Why is its strength tuned so precisely that galaxies could form before it took over? If it were slightly stronger, the universe would have been torn apart before stars and planets ever had the chance to form. If it were weaker, the cosmos might have collapsed in on itself. The fate of everything depends on what dark energy does next. If it remains constant, the universe will expand forever, growing colder and emptier as galaxies slip beyond reach. If it grows stronger, it could one day tear apart galaxies, stars, planets, and even atoms in a doomsday annals known as the Big Rip. If it weakens or changes form, the universe might experience new and unexpected phases of evolution, perhaps even cycles of rebirth. Beyond our horizon, different regions of space may already be experiencing these alternate fates, shaped by variations in dark energy's strength. Some areas might be collapsing while others expand violently, creating a cosmic patchwork of destinies. The strangest part of dark energy is that it is everywhere, flowing through every corner of space, even the emptiness between your hands as you read these words. It is not just out there, it is here now, shaping reality on the grandest scales, and yet it remains invisible, undetectable, except through the way it bends the universe itself. In many ways, dark energy is the most terrifying reminder of how little we truly know. We live in a cosmos where 70% of everything is a mystery, and yet that mystery holds the key to our ultimate fate. Will the universe end in silence, ripped apart by the very fabric of space? Or will dark energy shift into something new, rewriting the story of existence once again? For now, we can only watch, measure and wonder as the invisible hand of dark energy continues to pull the universe into an ever-accelerating future. If the vastness of the universe humbles us with its size, then the smallest scales of existence challenge us with their strangeness. Beyond galaxies, beyond atoms, even beyond the subatomic particles we know, lies a realm where space and time themselves begin to flicker and boil. This is the domain of the Planck scale, the unimaginably tiny dimension where the smooth fabric of reality dissolves into a chaotic sea known as quantum foam. Here the laws of physics as we understand them break down, and the universe becomes a storm of uncertainty. The Planck length, about 10 mixture-p meters, is so small that comparing it to an atom is like comparing an atom to the size of the visible universe. At this scale, distance itself stops behaving like a continuous line and begins to jitter in unpredictable ways. Space is no longer flat and steady, but wrinkled and turbulent, a frothing ocean of fluctuations. Time, too, loses its familiar flow, breaking into quantum ticks that defy any ordinary sense of cause and effect. In this microscopic storm, particles and energy appear and vanish spontaneously, borrowing existence for fractions of a second before dissolving back into the void. This bubbling chaos arises from the principles of quantum mechanics, the uncertainty principle, which tells us we cannot know both the position and momentum of a particle with perfect precision, also applies to energy itself. Even in a vacuum, what we would call empty space, quantum uncertainty allows energy to fluctuate. These fluctuations manifest as pairs of virtual particles that pop into existence and annihilate almost instantly. Under normal conditions, these events cancel out too quickly to notice, but at the Planck scale, they dominate reality. The result is a universe that is anything but smooth at its deepest foundations. What makes quantum foam even more fascinating is that it may be the birthplace of everything. During the earliest moments of the Big Bang, when the universe was smaller than a proton, quantum fluctuations in this foam were stretched by cosmic inflation into the seeds of galaxies. The tiny ripples of uncertainty became the blueprint for the cosmic web we see today. In this sense, every star, every planet, and every living being is the descendant of random fluctuations in the quantum froth of existence. Our entire reality is built on the jitter of something smaller than imagination. But quantum foam is not just a curiosity about the past. It may also point toward the future of physics. At these scales, gravity and quantum mechanics collide. General relativity describes space-time as smooth and continuous, while quantum mechanics insists that everything is uncertain and granular. The Planck scale is where these two great theories clash, where the equations of Einstein and Schrödinger no longer work. To fully understand this realm, scientists seek a theory of quantum gravity, a framework that unites the cosmic with the microscopic. String theory and loop quantum gravity are two leading candidates, and both suggest that space itself might be composed of fundamental units, tiny loops or vibrating strings that give rise to everything we perceive. Perhaps the most unsettling idea of all is that quantum foam might not just underpin our universe, it might be capable of generating entire universes of its own. Some theories propose that new universes bubble up spontaneously from the quantum foam, inflating into full-fledged realities, just as ours did. If true, then the frothing chaos at the smallest scales may be endlessly spawning new worlds, a cosmic factory of creation humming beneath existence itself. From the largest galaxies to the smallest quarks, reality is shaped by the restless fluctuations of this hidden storm. Quantum foam is the reminder that even emptiness is not empty, that beneath the calm surface of space lies a furious churning sea. It is strange, alien and impossible to visualize, yet it may be the most fundamental aspect of reality. Every star above, every breath you take, every thought you have is woven from its restless energy. At the edge of knowledge, where space and time themselves begin to dissolve, quantum foam whispers the deepest truth of all. Reality is not what it seems. We live our lives in three familiar dimensions of space: length, width, and height, and one of time that flows relentlessly forward. These four dimensions shape every moment of our experience, and it feels impossible to imagine reality working any other way. Yet the deeper physicists probe into the foundations of the universe, the clearer it becomes that our three-dimensional space may not be the whole story. Hidden dimensions could exist all around us, unseen and yet fundamental, shaping the forces of nature and possibly holding the key to mysteries like dark matter, dark energy, and even the origins of the universe itself. The idea of higher dimensions began as a mathematical curiosity in the early 20th century, when Theodore Kaluza and Oscar Klein proposed that adding an extra dimension to Einstein's equations of gravity could elegantly unify gravity with electromagnetism. While the concept was largely forgotten for decades, it returned with force in the late 20th century with the rise of string theory. In string theory, the basic building blocks of reality are not point-like particles, but tiny vibrating strings, and these strings can only exist consistently if space has more than three dimensions. Depending on the version of the theory, the universe might have 10 or even 11 dimensions. So why don't we see them? The prevailing explanation is that these extra dimensions are compactified, curled up so tightly that they are invisible to our senses and our instruments. Imagine a garden hose viewed from far away. To the naked eye, it appears one-dimensional, a simple line, but up close, you see that it has width, a circular cross-section wrapped into a cylinder. Similarly, our universe may look three-dimensional at human scales, but on scales smaller than atoms, additional dimensions could be tightly rolled up, hidden from view. Within those dimensions, strings vibrate in different ways, giving rise to the variety of particles and forces we observe. Some theories, however, suggest that extra dimensions are not small at all, but vast, perhaps even infinite. In these models, our universe is like a sheet or brain floating in a higher dimensional space called the bulk. All the matter and light we see is trapped on this three-dimensional membrane, but gravity, the most mysterious of the forces, can leak into the higher dimensions. This could explain why gravity is so much weaker than the other forces. It is not confined to our universe, but spread across additional dimensions we cannot access. If this is true, there may be entire parallel brain worlds existing just millimeters away from us in directions we cannot perceive, invisible but real, living out their own cosmic histories alongside ours. The implications of higher dimensions are staggering. They could harbor alternate universes with different laws of physics, entire realities layered beside our own. They might explain puzzles, such as why dark matter behaves as if it exists, but cannot be seen. Perhaps it is ordinary matter existing on a parallel brain, casting only its gravitational shadow into our universe. In some scenarios, collisions between brain worlds could even have triggered the Big Bang itself, with the energy of two universes colliding, creating the fiery birth of everything we know. But higher dimensions also challenge our very sense of existence. Just as a two-dimensional being on a flat sheet of paper could never conceive of up, we may be blind to directions and possibilities that exist beyond our three-dimensional perception. If beings could exist in higher dimensions, they might look down on our universe as a flat shadow, seeing the whole of time and space as a single object. To them, our past, present, and future might all be visible at once. The flow of time nothing more than a dimension we move through without realizing. Though we cannot yet see these hidden dimensions directly, scientists are searching for hints. Particle accelerators like the Large Hadron Collider may reveal subtle effects that point toward extra dimensions. Gravitational wave detectors might pick up vibrations leaking from higher dimensional space. And if dark matter truly is matter from a neighboring dimension, then its ghostly presence may already be telling us that our universe is not alone. Higher dimensions remain a mystery at the edge of science, but they offer an exhilarating possibility that reality is richer, deeper, and more layered than anything we can perceive. The universe we know may be just a thin slice of a grander, multidimensional reality, one where infinite possibilities unfold beyond our reach. If that is true, then every discovery we make is only the beginning of a far greater journey, one that will force us to rethink not only the universe, but our place within it. As if the idea of hidden dimensions were not mind-bending enough, string theory introduces something even stranger. The possibility that the universe we live in is just one solution among an unfathomable number of possible realities. This idea is known as the string landscape, and it suggests that the laws of physics we take for granted may not be universal at all. Instead, they may be local rules that apply only to our cosmic neighborhood, while countless other universes operate under entirely different sets of laws. If true, the string landscape doesn't just change how we see the cosmos, it redefines what we mean by reality itself. String theory begins with a simple but radical premise, that the smallest building blocks of the universe are not point-like particles, but one-dimensional vibrating strings. The way these strings vibrate determines what kind of particle they appear to be, whether that's an electron, a photon, or a quark. But for the mathematics to work, string theory requires extra dimensions of space, 6 or 7 in addition to the 3 we experience. These hidden dimensions must be compactified, folded into intricate shapes, so small we cannot detect them directly. And it is in the folding of these dimensions that the string landscape is born. Different ways of curling up these extra dimensions create different physical laws. One arrangement might produce a universe where electrons have the mass they do in our reality, while another arrangement might give them a different mass, or even prevent stable atoms from forming at all. One compactification might allow for stars and galaxies, while another might create a universe dominated by black holes or featureless radiation. Each possible folding corresponds to a different vacuum state, and string theory suggests that the number of these possible states is mind-bogglingly large, around 10 to the 500th power. To put that in perspective, that is more than the number of atoms in the observable universe. Each of those solutions could represent an entire universe with its own unique physics. The implication is staggering. Our universe, with its precise balance of forces and particles, is not uniquely privileged, but just one option among an unimaginable cosmic library. Why then do we live in this particular universe with these particular laws? The answer might lie in something called the anthropic principle. Out of the vast string landscape, most universes cannot support complexity, let alone life, but in some rare pockets, the laws line up just right, allowing galaxies to form, stars to burn, and chemistry to unfold in a way that makes life possible. We find ourselves in one of those rare universes simply because it is the only kind where beings like us can exist to ask the question. This idea is controversial, even among scientists, because it suggests that many of the constants we see in physics, the strength of gravity, the speed of light, the charge of the electron, might not be fundamental truths, but accidents of cosmic geography. They are local features of our universe's position in the string landscape, not universal facts of reality. If this is true, then asking why the universe is the way it is may be the wrong kind of question. The real answer might be because countless other universes exist where it is different, and we happen to live in one where the conditions allow us to survive. Some physicists search for ways to detect signs of the string landscape. Collisions between universes might leave scars in the cosmic microwave background, subtle imprints of other regions of the multiverse brushing against our own. Others look for hints in high-energy particle experiments, searching for deviations that could point toward hidden dimensions or exotic physics spilling into our reality. For now, the evidence remains elusive, and the landscape remains a theoretical frontier. Yet, the mere possibility changes everything. It means that reality may not be governed by a single set of physical laws, but by an ocean of possibilities, each as real as ours, but forever beyond our reach. It means that the universe is not fine-tuned for life, but that life emerges only in those universes where the tuning happens to work. And it means that what we call the universe may be nothing more than one island in an infinite archipelago of realities, each shaped by the hidden geometry of dimensions we cannot see. The string landscape is not just a scientific hypothesis, it is a philosophical revolution. It challenges the notion of a single reality and replaces it with a vision of endless diversity, where everything that can exist does exist somewhere in some form, whether or not we ever prove it. The string landscape forces us to confront the possibility that the cosmos is far larger, far stranger, and far richer than we ever dared to imagine. Standing at the end of this journey through the deepest mysteries of the cosmos, we are left with a realization both humbling and electrifying. The universe we see is only a fraction of what truly exists, and beyond the limits of our perception lies a reality more vast and more bewildering than anything we can fully comprehend. We began with the observable universe, that shimmering sphere of galaxies and light stretching 46 billion light-years in every direction. But the deeper we probed, the more it became clear that the edge of our sight is not the edge of existence. It is only a horizon, a boundary imposed by the speed of light and the age of the cosmos, beyond which entire realms unfold in silence, hidden forever from our eyes. These unseen regions may contain countless galaxies, stars and planets, each blazing with their own stories, each carrying possibilities that may never touch our own. And yet, through the faint whispers of ancient radiation, the patterns of dark matter, and the mathematical language of physics, we catch glimpses of these hidden expanses, like shadows cast on a wall by something unimaginably larger beyond the flame of knowledge. What strikes most deeply is how fragile our understanding is compared to the immensity of reality. We live in a universe where most of its content, dark matter and dark energy, remains invisible and unexplained, where the laws of physics may change from one cosmic domain to another, and where even the fabric of space and time could dissolve into quantum foam at its foundations. Our existence hangs delicately on conditions that appear fine-tuned: the strength of gravity, the balance of forces, the density of dark energy. Change them even slightly, and no stars would shine, no atoms would bind, no life would ever awaken to ask the questions we now ponder. Does this fine-tuning speak of purpose? Or is it merely the inevitable result of a multiverse where every possibility unfolds somewhere, and we happen to live in one of the rare universes that works? The answer may forever remain out of reach, but the question itself reveals the wonder of being conscious in such a strange reality. Even more unsettling is the possibility that the universe has no single fate, but many. If dark energy continues its relentless push, galaxies will recede into the dark until only black holes remain, slowly evaporating over unthinkable spans of time, leaving a universe cold and silent in heat death. If dark energy grows stronger, the cosmos could be torn apart in a big rip, shredding galaxies, stars, planets, and even atoms themselves. If vacuum decay lies ahead, Our universe might vanish in an instant, its laws rewritten into something alien, its structures dissolved without warning. And yet, there are models that suggest renewal, that new universes may be born from the ashes of the old, that quantum foam may forever bubble new realities, that what we call an ending is only another beginning in an infinite cycle of creation. The sheer scale of what we have explored, the idea of parallel universes drifting like bubbles in an eternal multiverse, higher dimensions folded invisibly beside our own cosmic webs, stretching across billions of light years, and realms of exotic matter and physics beyond imagination, makes human life feel impossibly small. And yet, there is a strange beauty in that smallness. Against this backdrop of infinity, we exist as conscious beings capable of asking these questions, capable of imagining realities that may be forever hidden from us, capable of turning mathematics and observation into glimpses of truth. We are stardust that has learned to wonder. That, perhaps, is the most extraordinary fact of all. In the end, the edge of the universe is not a wall but a mirror. It reflects our own curiosity, our drive to seek what cannot yet be known, our refusal to stop asking even when the answers may lie forever beyond reach. The horizon is both a boundary and an invitation, whispering that there is always more, always deeper mysteries waiting in the silence beyond the stars. We may never cross that ultimate boundary, but the act of searching, of expanding the map of our understanding inch by inch, is itself the essence of being human. The universe does not owe us answers, yet it has given us the gift of wonder, and in that wonder we find meaning. Perhaps what lies beyond existence is not the point. Perhaps the true marvel is that we are here at all, peering into the abyss, daring to imagine the impossible. The cosmos is infinite mystery, and we are its storytellers. And maybe in the grandest sense that is enough.